It's a pleasure to be here with you all this evening. I feel like any presentation, there has to be at least one discussion regarding artificial intelligence, and I have the pleasure of giving you one of those this evening. Now, generally speaking, most presentations that I have seen fall into one of two categories. Either we talk about the impact and the effect that AI is having on our lives and is going to have on our future. Or, usually in a more academic setting, it'll be a deep dive on a very specific aspect of AI technology and what it means. We're going to do something a little bit different tonight. My goal this evening is to demystify what is it that's actually happening when I pick up that phone or look at that screen and there's an AI algorithm behind it. Now, it's a very ambitious task, but I'm going to walk through some of the key components and some of the actual underlying, some of the key components and the underlying breakthroughs in math and technology that have enabled us to be here today. Now, with any statistical or machine learning model, the general goal is to get from point A to point B given a certain set of inputs. And we may not have defined or know exactly what point B will be. However, the algorithm, given our inputs, will help us get there. A really good machine learning or statistical model can do that effectively, even if the input is disparate or, as we would call it, highly variant. Now, there's sort of two general things that differentiate neural networks, the family of algorithms behind AI, from other types of classical statistical or machine learning algorithms. The first one's quite interesting. In most statistical algorithms, as we go from point A to point B, it constrains us to go very directly in that direction. If we begin to get off the path or go a direction that looks like it's not correct, it pulls us back in. However, with neural networks, we're often allowed to go what appears to be the wrong direction for quite some time, if in that path we eventually find a way to get to point B, where we're supposed to be, more effectively and more consistently. Secondly, we are given many more paths to choose and to travel to get from point A to point B. This would technically be what we call adding a lot of parameters to our models, but it allows us many different ways and many different insights in those relationships to find where we're supposed to go. Now, neural networks in their general structure are supposed to operate similar to a brain. Neurons that trigger and fire, and then through that, we're able to generate an output. In the more basic format, it's useful and it's insightful, but has somewhat limited applicability. Now, research was done in the 1990s, and in one specific branch of neural networks, and that branch was called recurrent neural networks. And what they found was actually super interesting. What they were able to do was to, as they travel on a path from point A to point B, they were able to leave markers along the way. And what that marker allowed them to do is remember, when in solving that problem, not just what my input had been, but what the order of that input was. The reason this is important is because it allows us to sequence. We can begin to solve problems of sequence. Now, it doesn't take too much imagination to see the types of things that you can begin to address when you can answer problems related to sequencing. Language, like I'm speaking to you right now. I have notes in my back pocket with check marks along the way. That's a sequence, right? Video, that's sequence. Music, there's a lot of real-world application to an algorithm that can help you solve sequencing problems. This is really cool. It was really great. They developed something called the long short-term memory network, which had a lot of breakthroughs in natural language processing. But there is an issue in the scalability of this technology. And the issue was, every time that you wanted to solve a problem using this, you had to go through the entire sequence of input data. Now, if I simply have a short sentence, okay, like, for example, the quick brown fox jumped over the, and if I asked you for the next 3 words, you would say the lazy dogs, okay? Why would you say that? You would say that because, well, I know what the first 5 words were, right? And so therefore, I know what the last word was, and I can then answer what the next word will be. But here's the issue. What if I have a lot of data that I need to process? What if the data that is my input isn't just a single sentence? What if it's like an entire encyclopedia, or multiple encyclopedias, or like a terabyte of data? Well, that's a lot of work I need to do in order to figure out what comes next. How do we solve this problem? Well, in 2017, there's this paper that was written. I kind of like the title of it. It's called "Attention is All That You Need." And what these researchers figured out is that there's actually a way to solve these sequential problems and to change the way that you construct your neural network architecture so that you don't have to look at all of the input data in order to figure out what should come next in your sequence. You can actually just identify the pieces of information that are really relevant to answering that question, right? So if I repeat my sentence again, I know that there's going to be the, and then there's going to be brown, and there's going to be fox, and certain words in my input are relevant to helping me understand what should come next. This solved a major problem. A, it helped us to train models in parallel so that not everything had to be looped through many, many times. B, it reduced the amount of time that it took to compute the answer to our questions. Now, this is a huge breakthrough, and to this day, it's what's broadly and widely used and enables us to continue to research various types of architectures. It's the foundation for most architectures in artificial intelligence. But there is another problem, and the issue is this. How many people actually have the resources and the budget and the capacity to train their own neural network, transformer network, for their own personal use or their company's use? Not many. It's kind of a big job, right? Like, what do? Go buy some GPUs? I mean, there's probably some Bitcoin miners somewhere around. But what if we could share that knowledge? What we actually found around 2018, there was a model created called BERT, and what they did is they just took all the data they could find. They took all the data on the internet, and they said, we're going to train one huge model with all the context of everything that we can put into it. We're going to train it for a long time. And then, at that point, what we're going to do is we're going to let you take one little amount of input data and put it on like a hat, which is your specific use case. So you can take this huge model, you can add a little bit of data, which points this model to solve your problem, having seen the examples that you've given it with your small data set, but it has all the context of all the data that was put into it. You might be going, ooh, this kind of sounds, I see where this could maybe come into play. We're using some things today where we go and we ask it a question, and then suddenly it's answering with a lot of context behind it, right? Which is great, and we're getting close to where we are today. One final question remains, though. You're thinking to yourself, but like when I type something in, I'm not giving it data. I'm just like asking a question and getting an answer. Well, there's something else that came out recently. It was a final breakthrough that really has enabled a lot of research and a lot of application. And that was called, well, one-shot learning, few-shot learning, and zero-shot learning. And you're probably going, okay, one, few, zero. I kind of think I know what that means. What it is the ability, as opposed to actually having to take a small data set and put it on top of that large model, this large language model trained on all this data, what it is simply feeding the model an example in one-shot learning or a few examples in few-shot learning with instructions to say, solve this problem, and here's an example of how to do it. The research has been incredible. It is actually proven to be very effective at solving difficult problems with all the context of the data that was used to train the model. So These are a couple of the breakthroughs that have been that have really been important in getting us to where we are today. Hopefully next time you're looking at your phone or a screen and saying, I'm asking a question and it's generating a result, you now know, hey, this is what's going on behind the screen. So thank you very much.